We can check why the different state model gives the same transfer function in the end through this the formula here. So for given A, B, C model, we are going to get the transfer functions through this formula. And so suppose we have um, different realization like this. Okay, suppose we have A bar, B bar, and C bar, and we want to show, and this guy is same as this. But from here, we saw that the C bar is C P inverse. Okay, and the A bar was PA P inverse. You just simply plug in the expression that we found, and B bar is P times B. Okay, okay. So right, so from here, so I've got the same expression copied here, and here from here, Si minus Pa P inverse, you can see the equivalent expressions like this, because this I is P inverse. Okay, P times P inverse is identity, and so um, the expression inside this parenthesis can be written as Si P inverse minus Pa P inverse. Okay, so S is a scalar, so it can be put anywhere, and at P, identity P inverse gives you identity, so it's Si. And now you have a P in front and the P inverse at the back. So P times Si minus AP inverse. Okay, so that's why you have this here. Okay, and then next, now you have to take the inverse. Okay, of this expression. So when you take the inverse of product of three matrices, and what happens here? Basically, you have to swap the order. Now C, B, A, and inverse, like this. Okay, so you have to swap the order, and so first P inverse will be P. Okay, so that P and this P inverse will cancel, and then Si minus A inverse comes, and this one and P times P inverse times P gives you identity. So that's why you have C SIA inverse B. Okay, so for whatever the state model, you are supposed to get the same transfer function in the end. So we have unique transfer function for the given system, but you may have various realizations depending on the choice of state vector. Okay, so now let's look at the control canonical realizations. Suppose a transfer function is given to us. Okay, so you have input u and output y and g, and they are all in S domain. So I put S here. So this transfer function g of s is y of s over g of s. Okay, so when the transfer function is given this way, I want to find out a state model like this. Be u y equals cx. Okay, I want to find this a, b, c. Okay, by choosing a proper state vector. Okay, so there are three ways. When you choose x as xc, you see for control, you're supposed to get AC, BC, CC. So that's a control canonical realization. If you choose XO, then you will get A, B, C, O, right? And there's another one, XJ, then you're going to get A, B, C, J, okay? So I will tell you these two today, and I will get back to you these Jordan canonical realizations next week, okay? So suppose you have g of s. how would you get the control canonical realizations? So first step is to split this y over u into two parts like this. So you introduce some intermediate the variable z. Okay, so this z and z cancel out, and so you are going to get same transfer function y over u. Okay, but suppose now you have two parts. Okay, that come from this original transfer function y over u. Okay, and then also you split this the transfer function into two parts. Okay, the first one is so s plus 2 times 1 here. So you take this one, okay, and then you call this z, so is z over u. Okay, so this one is same as this, and here that's the y over z. So this one is same as this. Okay, so after introducing this intermediate variable 1 over s cubed 5s squared 4s plus 3, okay, so that's the identity, and then y over z, and that will be s plus 2. Okay, so you're going to use these two equations instead of just one equation here to get this control canonical realization. Okay, so from here, now we go to a time domain. I mean, that's what the realization is supposed to be, right? You are in S domain. Now you take this guy to the time domain. Okay, so if you just multiply in this x fashion, then now this guy times that would be s cubed 5s squared and 3z, okay, and u, okay, and s cubed times z. What is the time domain counterpart of s cubed times z? So that's triple dot of z, okay, and 5 s squared and z double dot, okay, 4 z dot 3 z is u of t. So they are now all in time domain. So we have the differential equations that corresponds to this transfer function z over u. And how about this one? Well, you will see that this y is y of t is s times z gives you z dot and 2 times z t. So we have another differential equations that comes from here. So now we have these two differential equations to get the canonical realizations. Okay, so I just rewrote the two equations here, and from here now we want to draw this block diagram. Okay, so how do you draw this block diagram? Okay, it's very easy, and we know how to draw the block diagram for this third order differential equations. I mean, you need basically three integrators, right? And now I have z here, and z double z dot, and z double dot, and z triple dot. Okay. So and this z triple dot is the combination of 1, 2, 3, 4 signal. Okay. So u comes from here with plus sign, and now you have to take this to the right hand side. Then you have minus 5 z double dot. So z double dot times 5 with negative sign. Okay, so it's u minus for z minus. Okay, so u here and the minus 5 z double dot 5 minus 4 z dot, and z dot comes here, and 4 with negative sign minus 3 z here, and 3 negative sign. Okay, so that takes care of the first equations. And how about second equations? And here comes y. You see, here is input u, and here comes output y. And basically, we try to relate this y and u. Okay, so here comes u and here comes y. And now we try to find a block diagram that represents these two differential equations. We just finished the first one. The second one is y, which is sum of z dot plus 2z. So z dot here, so this comes here now, plus 2z. Z is here, and so you just multiply the signal with 2. Okay, so you just add these two signals to get this y. Okay, so we just found the block diagram, okay, to relate the input and output. And then next, how would you get the state model from here? Okay, to get the state model, basically we need this kind of expressions here. Okay, so to get that, we introduce a state variable, say x1, just after the integrator here. Okay, here's the integrator. You just introduce your state variable here. Okay. The reason why we are doing this is that that will facilitate the expression for x1 dot. Okay. So if this is x1, then this is going to be x1 dot. Okay, because this is integrator, right? So you just define this variable right after this integrator, and so the variable just before this integrator must be x1 dot. Okay, and then now you introduce x2 here again right after the second integrator, and x3 will be here, and that will be the right after this third integrator. So you introduce x1, x2, x3 from left to right. Okay, this order of definition is quite important. If you define the state variables in a different way, then you end up with a different state model. Okay, so what is x1 dot? X1 dot would be what? 5 times x1, okay? 5 times x1 with negative sign, so minus x1. And how about this? 4 times x2 with negative sign. And this one, x3, and 3 times x3 with negative sign. And we have plus u, okay? So that's the expression for x1 dot. How about x2 dot? x2 is here, and so this would be x2 dot. But x2 dot is exactly x1. Okay, so x2 dot will be simply x1. How about x3 dot? x3 dot is here. Okay, x3 dot will be x2. Okay, so you have these state equations. And how about y, output equation? Output y is sum of x2 plus 2 times x3. Okay. So this is state model. Okay. What was the transfer function? The transfer function was here. Okay, so that was s cubed for s 3 and 3 plus 2. And this was the transfer function. Okay, and now we have state model like this, but we have to write this in matrix form, and x dot, the matrix form will be minus 4 minus minus 5, minus 4, minus 3, and 0, and not 0, sorry. It's 1, 0, 0, 0, 1, 0. Okay, have x. And plus u. So 1, 0, 0, u. Okay. How about y? Y is y is 0, 1, 2, 1, 2 x plus 0 u. Okay, so we have AC, I have BC, and I have CC. Okay, and I have DC. Okay, so we have ABCD matrices. Okay, so what is special about these realizations? Now, by comparing this state model with transfer function, you can see that these 5, 4, 3 appear in the first row of A matrix with negative sign. Okay, so 5 goes to minus 5, 4 goes to minus 4, and 3 goes to minus 3. So that appears in the first row of A matrix. And how about this? S plus 2, I have 1, and you might have S square in the numerator, but now its coefficient is 0. So that's why this one doesn't appear in the numerator. So now I have 0, 1, 2, and these constants appear in C matrix, right? So we've got this state model through quite complex job. Like we drew this block diagram to get the state model, but actually you don't have to draw this block diagram to get the state model. You can get it directly from the transfer functions. You look at the denominator and take all the constant, okay, except the highest one, 5, 4, 3, now comes in the first row of A matrix, and then 0, 1, 2, okay, which are the constants of the numerator polynomial, and then you can simply put those in the C matrix, okay, and all the other numbers are just the same as for all cases, like this 1, 0, 0, okay. So suppose you had 4 by 4 A matrix, then you are going to get 4 by 1 B matrix. In that case, you're going to get 1, 0, 0, 0. Okay, so B matrix is always 0 matrix except the first entry where 1, okay, 1 is placed. And how about all the other rows of A matrix? Here you have 1, 0, 0, next line 0, 0, 1, 1, 0. Okay. If we had 4 by 4, then you could have non-trivial first row, and second row would be 1, 0, 0, 0. Third row 0, 1, 0, 0, and the last one 0, 0, 1, 0. So this is called the main diagonal, and this one is called sub-diagonal. So you can see this sub-diagonal entries got all 1. I mean, that's the structure of A matrix, AC. Okay, BC was simply 1, 0, 0, 0. Because 0, the vector with non-zero entry, okay, at the first, okay, place. Okay, that's just 1. Okay, so this structure is always the same for all cases. Okay, when you convert whatever transfer function to a state model in control canonical form, you are going to get the B matrix, which has exactly 1, 0, 0, 0, 0 structure. And this AC, if you look at AC, then all the sub-diagonal entries got the common 1, except basically the first row. Okay? The first row is determined um, by this denominator, the polynomial. Okay, so that's what I'm saying here. Okay, so first row and this sub-diagonal entries and this 1 is always there except all the other 0 entries in B matrix, and the C matrix comes from the numerator of the transfer function. Now we are looking at observer canonical realizations for these same transfer functions. Previously we used some intermediate variable z to split this transfer function into two parts. But now we are directly to multiply y and this the denominator of transfer function to get this left hand side, and we multiply u and the numerator of transfer function to get right hand side. Once you have this, then you divide the whole equations by the highest power of s. So this one becomes y, and this one becomes 5 times 1 over s squared, etc. Okay. Once you have them, then you take all these terms here except just y. Okay. You just have y remained in this left hand side. You take all the other terms to the right hand side. Right. And then you just combine, say, this one and this one, which has 1 over s cubed involved. You combine this one and this one, which has 1 over s squared involved. Okay, it has the single 1 over s term. Okay, so you have the left hand side y, and right hand side you are going to have this. Okay, so this term here has 1 over s cubed and 1 over s squared and 1 over s. Okay, so you have this kind of situation: a square b plus c, right? And now I'm going to take 1 of s to the front because 1 of s is a common factor of these three. Okay, square a plus 1 of sb plus c. Okay, maybe you can just switch the order as 1 of sb plus s square b, and these two has again the common factor of 1 of s, c plus 1 of s, sorry, c, and b plus 1 of sc. Okay, something like this. A should be a. So this is basically c, and this is the b, and this is a. Okay, so why are we doing this? Because we are going to use only 3 integrators in the end for the representation of these third order transfer functions. We could represent these transfer functions with these expressions, but this will end up with 1, 2, 3. So in total, we are going to use 6 integrators for the representations, which is not minimal representation. We want to use the minimum number of integrators for the representations. Okay, so once you have this, then now we can draw the block diagram here. Okay, so here comes output y. Okay, you have input u. Okay, so we are going to relate this u and y, okay, using this block diagram. Okay, So here comes the way of defining state vectors. Now here y becomes x1. Y becomes x1. So the whole thing here, so that will be x1. Okay. But then here is one of s. So basically you define x1 right after this integrator. So this is integrator. You define x1 right after this one of x. So this is going to be x1 dot. And this one is exactly x1 dot. Okay, so everything that comes after one of s here will be x1 dot. It's not x2, it's simply x1 dot. Okay, now how do you define x2? Well, x2 is now this one. Okay, so this one is x1, and so everything that comes after one of s will be x1 dot. Okay, and now x2. Now you call this x2. Yeah. Okay, so this is now called x2, and actually here comes x2, and that is defined right after one of s, like here. Okay, so if this is the whole thing is x2, okay, then x2 plus minus 5y, okay, so minus 5y will be x1 dot. Okay, so here x1 dot is minus 5 plus x2. The whole thing is x2. I mean, this is just a way of defining state variable. Okay, so x2 here and 5 times x1, okay, with negative sign will be x1 dot. Okay, so that makes sense. Okay, so so the whole thing is x1, and so x1 is defined right after this integrator, and just before this integrator it will be x1 dot. Okay, so everything inside this parenthesis, square bracket, that will be x1 dot, and x1 dot is minus 5y plus everything here, and that is defined as x2. Okay, so if this is x2, then so this one here, again, everything inside this second bracket here, that will be x2 dot. Okay, because x2 is defined right after this integrator, and so the one just before this integrator will be x2 dot. So this will be x2 dot. x2 dot is sum of these two parts here. So x2 dot is minus 4y plus u. So here y was here, which is x1. So y1 times 4 with negative sign, okay, plus u. Okay, u comes here. Okay, so this one is basically minus 4y plus u. Okay, and then we need this. Okay, so this one now is called x3. Okay, so this one, so s1 times minus 3 plus 2u, that is defined x3. Okay, so this guy plus x3 will be x2 dot. Okay, so this one x2 dot. x2 dot will be this guy plus this one here, and that is defined as x3. Okay, so x3 comes here. Right. So now I just define this x3. Okay, and this one here is now called x2 dot. Okay, so again, the whole thing is x3, and x3 is defined just before the integrator, right? So x x3, so this x3, so if this is x3, then this is going to be x3 dot uh, right, so this is x3 dot, and this x3 dot is sum of minus 3y plus 2u. So with negative sign, okay, 3 times y plus 2u, 2 times u. Okay, so that's how you define this state variable x1, x2, x3. Okay, is quite complicated, much more complicated than the control canonical realization. Okay, but let's just go ahead and look at the state model corresponding to this state vector. Okay, so x1 dot, so this is x1 dot here. So x1 dot is minus 5x1, okay, plus x2. And x2 dot, and here comes x2 dot. x2 dot is minus 4x1, 4x1 plus u, plus x3. Okay, x3 comes. And x3 dot here, that's minus 3x1 plus 2 times u. Okay, and obviously y is equal to x1. Okay, if we put this guy in matrix form, then you have minus 5, minus 4, minus 3 being multiplied with x1. And so the first column of A would be minus 5, minus 4, minus 3. Okay, and now because of x2, x3, you are going to have 1, 1 on the super diagonal. This is called the super diagonal. This is the main diagonal, sub-diagonal, and the super diagonal. So you're going to have super diagonal terms equal to 1. Okay. How about the B? So here comes 0u, and so 0, 1, 2. So you have 0, 1, 2. And C, so that's y is equal to x1, so it's going to be 1, 0, 0, x. So that's why you have 1, 0, 0. Well, I mean, this is quite interesting discovery because this AO, the A matrix for this observer canonical realization, is in fact the transpose of this AC. So this first row now becomes first column, right? The second row becomes second column. Okay, the third row becomes third column. So AO is in fact AC transpose. Okay, so you're going to have non-zero, okay, non-trivial first column. Okay, that comes from where? That comes from here, denominator of G of S, right? And how about this? The B matrix is 0, 1, 2, and this BO is exactly the C matrix here, right? The transpose of the C matrix. So this is a C transpose. How about CO? CO here is 1, 0, 0. 1, 0, 0 was a transpose of this B matrix. So it's BC transpose. Okay. The first column of AO comes from denominator of the transfer function. The B matrix here, 0, 1, 2, comes from the numerator of the transfer function, and all the other entries are just the fixed. I mean, they have just the fixed structure. As I said, this A matrix will have all ones on its super diagonal. Remember, we had all ones on the sub diagonal for the AC, but AO, you're going to have this 1 on the super diagonal. And the C matrix will be always 1, 0, 0, 0, 0. Just the first entry will be 1, and all the other terms will be 0. Okay, because we always get y equals x1. Okay, for whatever transfer functions, okay, you are going to define your x1 as your output. So that's why CO will be 0 matrix except the first entry, which is equal to 1. Okay, and although the way of the getting these block diagrams are totally different if you compare this observer canonical form and control canonical form, right? But these two realizations have this beautiful relationship. This is called duality. Okay, and you are going to see this, the duality, when you design control and observer. Because this observer canonical form will be used for observer design, and the control canonical form will be used for control design. And these two different, totally different designs are related through this beautiful duality relationship. And this is it for the lecture 4.